This is a video from section 3.5. The directions say to use implicit differentiation to find the equation of the tangent line to the curve at the given point. On 29, we have x to the 2/3 plus y to the 2/3 equals 4, and the point is negative 3 root 3, 1. To get the equation of the tangent line to the curve at the given point, we need to know the slope of the tangent line to the curve at the given point. How do we do that? We need to look for dy dx. So we're going to differentiate both sides of the equation with respect to x. So the derivative of x to the 2/3 plus y to the 2/3 with respect to x is equal to the derivative of 4 with respect to x. The derivative of any constant is 0, so we get 0 on the right side of the equal sign. On the left side, the derivative of x to the 2/3 is 2/3 x to the negative 1/3. That's just power rule. Plus, the derivative of y to the 2/3 with respect to x is 2/3 y to the negative 1/3 dy dx. That's chain rule. So now I'm going to move this first term here over to the other side. So 2/3 y to the negative 1/3 dy dx is equal to negative 2/3 x to the negative 1/3. If we divide both sides by 2/3 y to the negative 1/3, I get dy dx is equal to negative x to the negative 1/3 divided by y to the negative 1/3. But I could rewrite dy dx as follows. Dy dx is negative y to the 1/3 divided by x to the 1/3. Now, 3 root 3, by the way, is equal to 3 times 3 to the 1/2, which is equal to 3 to the 3/2. So I'm going to need that. So I'm going to evaluate dy dx at the point negative 3 to the 3/2. So basically, I just rewrote negative 3 root 3. Okay. So evaluate dy dx at negative 3 to the 3/2, 1. And so the first coordinate is x. The second coordinate is y. So I'm going to replace y with 1 and x with negative 3 to the 3/2. And when I do, I get dy dx is equal to 1 over root 3. And again, that's at the point negative 3 to the 3/2, 1. So we're given a slope of 1 over root 3 and a point negative 3 root 3, 1. The tangent line, we can write the equation as y equals mx plus b. This is just slope-intercept form. We already know that the slope is 1 over root 3. So I'm going to replace m with 1 over root 3. So y equals 1 over root 3x plus b. When x is negative 3 root 3, y is equal to 1. So 1 is 1 over root 3 times negative 3 root 3 plus b. Solving for b, I get b equal to 4. And thus, y equals 1 over root 3x plus 4 would be the equation of the tangent line. That's how we do problem 29. On problem 30, we have x squared 31. We have x squared minus xy minus y squared equals 1. The ordered pair here is 2, 1, and we want the equation of the tangent line. Differentiate both sides with respect to x. And so we're taking the derivative of x squared minus xy minus y squared with respect to x and setting it equal to the derivative of 1 with respect to x. Now, the derivative of x squared is 2x. The derivative of xy by the product rule, so I'm going to go 2x minus the quantity x dy dx plus y times the derivative of x, which is just 1, minus 2y dy dx, and that's equal to 0. And by the way, 2y dy dx is just the derivative of y squared. So if I solve for dy dx, I get y minus 2x divided by negative 2y minus x. Okay? Now, dy dx at the point 2, 1, remember the first coordinate is x, the second coordinate is y. You're going to get 3/4. So we're given a slope of 3/4 and a point 2, 1. Y equals mx plus b. The slope is 3/4, so I'm going to replace m with 3/4. So y equals 3/4 x plus b. But remember, when x is 2, y is 1. So I'm going to plug that information in on the last line and solve for b accordingly. So 1 equals 3/2 plus b, so b is negative 1/2, and I'm done. So y equals 3/4 x minus 1/2. And that's the equation of the tangent line for problem 31. For problem 33, I have x squared plus y squared equals 2x squared plus 2y squared minus x to the second, and the ordered pair is 0.5. So I'm going to do the same thing. I'm going to differentiate both sides with respect to x. And so 2x plus 2y dy dx is equal to 2 times 2x squared plus 2y squared minus x to the first times the derivative of this inside function that I'm circling with respect to x. The derivative of that inside function is 4x plus 4y dy dx minus 1. Now, you might notice it's pretty inconvenient to solve for dy dx as compared to the first two problems. So I'm going to show you a slightly different approach here. Remember that you're wanting the equation of the tangent line, but we need to get the slope first. So we want the slope of the tangent line at the point 0.5. So we don't want to lose sight of that. Now remember, when x is 0, y is 1/2. And so I'm going to plug that information in up here. And so if you notice, 2 times 0 plus 2 times 1/2 dy dx is equal to 2 times the quantity 2 times 0 squared plus 2 times 1/2 squared minus 0 times the quantity 4 times 0, x is 0, right? Plus 4 times 1/2 dy dx minus 1. Okay? It's much easier to solve for dy dx on this line compared to solving dy dx when there's solving for dy dx when there's a lot of x's and y's involved. So you might notice here I get dy dx down here is equal to 2 times the quantity 2 times 1/4, 1/2 squared is 1/4, times 2 dy dx minus 1. So it looks like dy dx is equal to 2 dy dx minus 1. So at the point 0.5, dy dx is 1, and that's going to give me the slope of the tangent line. So we're given a slope of 1 and a point 0.5. Now remember, the equation of a tangent line in slope-intercept form is y equals mx plus b. But we know m is 1. So if I plug that in, I get y equals 1x plus b. When x is 0, y is 1/2. So that tells me b is 1/2. And that tells me that the tangent line is y equals x plus 1/2. And that's going to do it for this video for section 3.5. And we worked problems 29, 31, and 33. Thank you.